So, nice. Okay. So, today I'll be talking about doing some detection of exoplanets via machine learning and neural networks. So I've been working with this on this project with Space Lab for past year. It's been mostly on and off. I'll talk a little bit about the Space Lab. It's not to be confused with NASA Space Lab. We are an open source project group. It's based on it's actually based on the founder Matt's bootcamp project from quite a while ago. Since then, he's decided to try to bring it up as what he calls a people incubator. So people hop in, work on some projects, hop out, and we help each other while the projects are ongoing. So the status right now is that it's a nonprofit organization, and currently we're working on this exoplanet detection project. Because it's a kind of a side project, come as you go. Because the year might not be as much work as you think it is, but there's also pretty heavy research in this field. So anything that we haven't worked on, there's been extensive research on as well, and I'll cover that as well in the presentation. So one last thing, shout out to Space Lab. You can find us at spacelab.space, and there's some blog posts there if you want to check that out as well. And of course, if you're interested, I'm always happy to make warm introductions. So short thing about me, I graduated 6 years ago from the University of Waterloo in Ontario. Since then, I've been mostly working as a data engineer. So been working for about 6 years, and I started this project with Space Lab about a year ago. And as Larkin said, my real day job is at Google. I do I mostly do data engineering work for their GCP sales pipelines. Cool. So let's talk about the actual detection now. So the core problem that we're trying to solve is that a bunch of light data comes in from NASA's exoplanet missions. So these are missions like TESS and Kepler. But this data is, one, is messy, and two, we want a way to actually confirm whether or not this data actually comes from planets or some other sources. So I'll go a bit into this, and you'll see what I'm talking about in a second. So let's first define some terms. An exoplanet, what we're looking for is basically a planet outside the solar system orbiting an extrasolar star. So we know they exist because they cross the star at specific transits. These are called TCEs, or threshold crossing events. And you can kind of see in this illustration that there are some planets that will pass through our field of view with the star, right? And this will block some of the light. This actually also happens in our own solar system, although from Earth, the only planets that are actually capable of blocking or of getting between Earth and the sun is Venus and Mercury, right? But if you look at astronomy news, the transit of Venus happened in 2012, and the last transits of Mercury were in 2016 and 2019. So it happens inside our solar system, it happens outside our solar system, and because it happens outside our solar system, we can use this difference in light data to find exoplanets. Something interesting I kind of share as a side is I found this cool illustration of Kepler 22b, which is kind of interesting because Kepler 22 is one of the systems found in the Kepler system, which is one of the source, one of the missions for the source data we're using. Kepler 22b specifically is a super Earth in the habitable zone. So what that means is it's a terrestrial planet like Earth, but it's bigger than Earth. This illustration, for the sake of the planets, is actually to scale. The other thing is that it's actually orbiting within the habitable zone. So it's kind of interesting for things like search for extraterrestrial life missions, and exoplanet detection is a large part of that. So other basic concepts. What is a light curve? So a light curve is a time series of flux values, as you can see plotted here. Basically, as I mentioned, during a transit, you should be able to see where that threshold crossing event is, right? And that's that drastic drop in flux. One thing to note is that this is normalized from -1 to 1, so that the threshold crossing event is a lot more obvious. But you can see after normalizing, there's a very easy drop in flux, and that's where the crossing happens. So the key problem here is that this is exoplanets are not the only thing that cause this dip, right? Things like binary star systems, when they eclipse each other, will also cause this dip, or will cause a similar dip. Things like equipment error can also cause this dip. And so the main goal of these inference networks is to detect which one of these dips are actually exoplanets and which one of these dips are instrument error or something else. So talk a bit about our data sources. So primarily, we've just worked with the light curve library in Python. So that's light curve with a K. And this library is useful because it has data for both the TESS and the Kepler missions. The TESS is the slightly TESS is the slightly newer one, where actually even professional astronomers are still working on exoplanet detection. It's light curve is also really useful because it downloads. It has an API for directly downloading from MAST, which is this Minkowski archive for space telescopes, which is usually where a lot of NASA data goes for, I guess, goes into the public domain. So actually, other interesting tidbit, like data for the James Webb Space Telescope is being put up there now. And yeah, if we didn't use this library, it would be a whole mess of HTTP requests and parsing. So the fact that this API exists makes our life a lot easier. So if you're getting started with this, I recommend looking into this library. The other thing this library does is it actually encapsulates a lot of small transformation functions for the transformations that I'm about to show you, which also is really helpful because a lot of the operations are pretty math heavy if you plan to do them yourself. So it's a good beginner to get started with transforming for light curves. Another source we have comes from Caltech IPAC. They have a program called ExoFOP, which is the Exoplanet Follow-up Observing Program, and this program is where we get other data. So data that's not about the light curve itself. These are things like different parameters about the star, such as mass, density, effective temperature. And also very importantly, we get data like the start time of the threshold crossing event, as well as like the period and the duration of the start of the TCE. So all of these things, start time, period, duration, you'll see they become important as we look into processing. You'll see that it becomes more important as we look into processing the light curve. One other thing to note is that the data is a FITS file. So I don't know how many of you have astronomy backgrounds, but it's usually open as an image file. You'll see it as the image on the lower right. But these are basically flux values at different pixel positions. And if you take this over a time series, which the light curve library will do, then you're able to create that time series flux value that we can later use to feed into the neural network. There's also some other data like the Centroid data, which I'll talk about in a bit as well. So, so yeah, the ExoFOP stuff, this is kind of messy, but I'll just kind of go over this. So the first thing you see is the first set of data that we're interested in is the epoch, which is the start time of the transit, and then the period and the duration of the transit. So that is all within the Caltech data. There's also these stellar parameters. Okay, so let's talk about cleaning a light curve. So I showed you this is what the cleaned light curve looks like. And actually, the light curve that we get from NASA or MAST looks like this on the left. So something you notice is one, it's periodic data, and that's because we haven't folded it yet. And it's evidently periodic data because the transits are periodic, right? Because they're in an orbit. Something else is there's a huge gap in the middle, and that's because that's caused by a multitude of reasons, but it's just possible that data is missing in the middle. Again, this is something we fix just by folding the periods over each other. Yeah, so anyway, the first step we do is we do the smoothing by just removing a 3 sigma of outliers. So anything outside of 3 standard deviations, as you notice, gets cut off and trimmed off. The other thing to note is that you may recall the light curve has this steep drop. I need to remind myself to not use my wheel, sorry. So this light curve has a steep drop. And what we would do is using the threshold crossing event duration transit start point. So using the threshold crossing event duration, start time, and period, we're actually able to find when this threshold crossing event happens and then place a mask over it. So during smoothing, we can ignore the transit portion of the data completely, just so we're not smoothing out this dip. Right. So again, after removing the outliers, the data will look like this, right? The more extreme points get removed. The next step is flattening, and this is when we remove the low frequency trends within the data as well. So usually this is done with spline fitting, but light curve uses something called a Savitsky-Golay filter. But functionally, it basically just removes like strong inconsistencies between the points in within the flux data. So whether you're using a filter or a spline, it's accomplishing the same thing. Right, and then left, right, before, after. One other thing to note is that if you're wondering what this TIC is, it's basically just identifying not the star, but the specific object of interest, which is the planet candidate. So TIC stands for TESS Input Catalog. So this is from the TESS mission, and this number, specific ID, right? Okay, so after flattening, the next step is folding, and this is where you see it actually start to become a light curve, and that's just us folding the absolute time into a phase, right? As you can see the change on the x-axis. But after folding it, you actually start to see that this is you start to see the very clear dip in flux at around phase 0, right? And the reason why it's always aligned at phase 0 is because we're able to do this again with the transit start time and the duration of the transit, so that we can line the dip of the light curve at exactly phase 0. And this is kind of important because again, all of this data is being fed the same way into the neural network. So we want the data that's fed into the neural network to be consistent. Yeah, and then yeah, okay, and then right, and then oh my god, sorry. And then the next step is binning all of this data. So this is when we take a multitude of points, and just to further reduce the noise in the source data, we take multiple points and just bin them into one point. And the number of bin points depends on the number of original points, But you can see it the drop in flux becomes a lot more clear here. And another note is that this is also where we do the normalization from -1 to 1. I guess this kind of just makes it's the last step to make the data ready to feed into our machine learning model. And yeah, I have like a line graph here, which makes things a bit more clear. You can very clearly see the drop now, right? So this is something called a global view, right? Which is the view of the entire transit and the area around it, or I guess the view of the whole data set, including the transit. Something else that we want to feed into our model is the local view, which, if you look at it, it's just a zoomed in snapshot of the transit. This is just something to bring up. Again, there's more points in the local view during the transit because we've zoomed in at the binning stage, and we've been with like less points per bin. So it's a more granular. It's a more granular representation of the light curve zoomed in at the threshold crossing event. So we have this global view and we have this local view of the light curve now. How do we calculate how do we identify its planetary status? So our initial problem is we have these raw signals now. And how do we answer the question, is this a planet? There's a lot of different models that are used to calculate this. But this one is from Dr. Andrew Vanderburg and Chris Chalou. This diagram is actually from a later paper, but it's similar in concept to the original astronet that they've created or they've published in 2018. One thing to the important thing to note about the astronet model is that the global and local views are being fed separately into convolutional layers, and then the result of that is there's max pool stages throughout, and the result of that is fed into fully connected layers. And in terms of the hyperparameters for this, most astronomers will just tell you it's trial and error. And I believe Dr. Vanderburg said the exact same thing. So I can't go in too much into that, but again, if you end up asking like why specific nodes are the way they are, it probably was just tested and ended up working well with those specific nodes. Important things to note is just the structure of the neural network. These scalar features I will actually go over in a bit. The output layer is a sigmoid output, so we'll get a value, or it's a sigmoid scaled between 0 and 1. So we'll get a score of the likelihood of this candidate to being a planet, and this will also be very useful for validation coming up. So the scalar features, this was not in their original astronet model in 2018. This was later added to try and use more of the information about the star to try and identify like the possibility of an exoplanet. The astronet model is not the only one that actually does this. So there are a number of stellar parameters that are usually used for this purpose, right? Things like effective temperature, surface gravity, metallicity, radius, mass, and density. These features are all numerical values, so they're usually normalized across the entire data set, and by that I mean just divide by or subtract the median and divide by the standard deviation, so you're always getting a value between actually, I guess not. You're getting a value that represents the distance from the standard deviation for the data set. Because of that, the units of these things don't matter as long as the entire data set is consistent with the same unit. This is Dr. Megan Anstell's ExoNet model, which which takes these stellar parameters into account, right? So if you look at the structure, it's also a series of convolutional layers into a series of fully connected layers. It's very similar to the astronaut model, but the difference is that these stellar parameters that were mentioned are fed in as extra inputs at the fully connected layer stage. The other thing to note is that the centroid data is now being fed in with the local and global views. And this centroid data is actually what is used to identify eclipsing binaries. So the centroid data looks like this, right? And there is also a local and global view for the centroid data. It comes with the FITS file that we get. This is also normalized to represent standard deviations from the mean instead of like an absolute value, which is why you see it go from I guess around -4 to 3. It should also mostly be periodic, right? Because the centroid that we're interested in is a fluctuated centroid. So what that is it's the center point of all of the data if you consider each flux in that pixel file to be a weight, right? Because the star and everything around it kind of operates periodically, you do see some periodic patterns around this as well. And again, this is very useful for identifying eclipsing binaries, and that is because of the knowledge here, which is actually shared by Dr. Anstel initially, which is the centroid behaves differently between an exoplanet and eclipsing binary, right? So for an exoplanet during a transit, you'll see a drop in the flux, but the light centroid wouldn't move because the planet is just basically a small dot that blocks off some of the star's light. But for a binary system, when they eclipse each other, you'll still see that drop in flux because one of the stars may have blocked some of the light from the other one. But the centroid of light will shift, right? Because it will shift towards the other source, right? So because of that, you'll notice like a huge shift in the position of the centroid. So because there's this like huge noticeable data difference, this is also fed into the neural network, and the neural network is actually able to pick up on this. Because according to some sources, eclipsing binaries account for up to like 30–35% of transit-like signals. Actually identifying this kind of eliminates a lot of false positives for exoplanet detection. So a bit about what we did. So this is using the ExoNet model and using the preliminary data from Dr. Anstel's working group. We actually were able to replicate this, get around their claimed 98% average precision and 97.5% accuracy. We also have like a pretty good precision recall curve. I couldn't tell you the area under it right now, but you can kind of eyeball it. Doesn't look too bad. But yeah, we mostly measured the precision and accuracy. It looks like we were able to get up to the claimed value, which is good. Because we haven't actually built our own network yet, we just mostly run data through ExoNet, and we're slowly working on iterating through it. Last thing I'll do, talk a bit about what Spacelab's infrastructure looks like here. And it's so most of this is kind of just planning. Oh no, here we go. So most of this, we wanted this to be serverless, and the reason for that is just money issues, right? We didn't want to pay for a dedicated server. And because it's serverless, this is all run with AWS Lambdas. So the parts right now that are very heavily run is just the ETL job that's doing a lot of the Lightcurve processing, that's fetching catalogs from TESS and Kepler for any new data coming in, and fetching new data from MAST and then cleaning that new data from MAST. So that is all called manually right now through Lambda. We are planning to, that would be these two parts here. And we are planning to add an event bridge trigger to it once most other things are done, so that we can schedule or we can run this on a schedule, possibly semi-annually for training and then more frequently for inference. The training, really, we are reiterating our own neural network to try to meet the same standards as the researchers' neural networks, AstroNet and ExoNet. And this, we will probably be spinning up or have Lambda spin up EC2 instance to do this. We are considering things like batch or EMR. Right now, all of this data is being dumped into a DynamoDB table, which may or may not be incorporated on the spacelab.space site. I'm not too sure yet. However, the end goal is make this available via a GraphQL API, or at least make it available via the spacelab.space API, sorry, make it available on an Explore page on the spacelab.space site, which actually is there right now, although I'm not sure if our model output is there. So if you want to give that a look, yeah, I invite you to. And that is my talk. I will now take questions. Cool, thank you for listening.
Questions? Lena? Ask away.
Hi, thanks for the talk. I'm not so sure I understood correctly your, I believe, 10th slide.
10th slide, okay. Let's see. This one?
Yeah, is it the data that you get initially, and then you are looking for this pattern of the light curve from there?
Yeah, so it's a good question. So one thing is this is the data that we get directly from our source, right, from MAST. So from the Mikulski archive. And what happens is NASA already identifies when, or I guess, identifies stars with these threshold crossing events, right? So you can't see it very clearly here, but you do see the drops. And that's kind of already been identified as like, hey, like there is something here. And our goal is just to clean this so that we can say like, hey, is this drop caused by equipment error? Is this drop caused by some other stellar factor, like, excuse me, like being an eclipsing binary, or is this actually caused by an exoplanet, right? The fact that we got this from MAST and the fact that there's like a TIC associated with it means that it's already been identified that this is a curve with a dip. Right, so we just need to clean this curve so that it looks like this, so that we can feed it into our input. Looks like this, so that we can feed it as input into our machine learning. Does that answer the question?
Not so much. I was confused by the x-axis because I'm not so familiar with
the
theme. And you have time there. So is it the same? So it's like a lot of light curves on one graph?
Yeah, it is basically like that. So I think it should be BJCD, but it's this number is actually just something like a barocentric Julian date or something like that. This scale is actually just in days, right? It's possibly from the start of the mission or something like that. But if you just look at the size of the scale, well, yeah, so this is a span of a few hundred days, right? From our perspective, this planet would orbit the star and have a transit every couple, or I guess every 50 days less, and that's kind of the period that we're seeing with this TESS object. So because it's periodic, right? Because planet is orbiting the star, we see this like light pattern repeat every X days, right? And then we fold it so that we get like we get data that's based on phase instead of this like absolute time. Does that make sense?
Ah, now I get it. Thank you.
Cool.
Any other questions?
Is there any other questions?
I have a question. So on the website, the Spacelab website, you guys have confirmed and false positive and candidate results. That's the output from this application, right?
That is also a good point. Actually, I didn't talk about how the data is split, which is a good point. So there's already some research being done on it. Some of this is not. Most of this is actually not done with neural networks or with machine learning in general. They're usually astronomers kind of looking at this data. And actually, so I can't give you an educated answer on what they do. But there's astronomers that actually work with a whole bunch of aspects of this data, and they and possibly even looking at it, and they confirm exoplanets through other ways as well. So the confirmed points. So I guess what I'm trying to say is a lot of these objects of interest actually come in from NASA with labels on them already, right? So the confirmed ones and false positives are already identified as are labels that are passed in from NASA. As I mentioned in our infrastructure slide, in this DynamoDB in the back, we initially store the NASA data, and then we use the output from our model to modify some of this data. So what you're seeing on the spacelab.space website, it's possible it's coming from NASA, or it's possible that it's coming from our internal model. Yeah, so basically the false positive and the confirmed planets, or for the purposes of our training, the false positives and the confirmed planets, they're ones and zeros for our training data. And then there's one more label like planetary candidate or possible planetary candidate. That's when NASA is not sure themselves, right? And that's when we put our own machine learning to use to try and categorize it into one of the planet, not planet categories, right? Things like Kepler 22b, like there's researchers at NASA who very specifically know for sure that this is a planet, possibly because they've even seen it.
So is this I can see two use cases.
Yeah.
I'm not an astronomist, but so one, you can go and use this to narrow down the search space for humans to search, right? I'm assuming you might want to use some AI to narrow down the subset of potential planets and then have astronomers kind of sort them out using their own knowledge. And they may reduce the search from, I don't know, 100 from 10,000 a day to 100 a day, which could be useful. For example, another use case could be literally humans cannot know if this is an exoplanet or not, but maybe a machine learning algorithm can do better than a human. So are these the use cases like that would come out of this technology?
Yeah, so in terms of like searching for extraterrestrial life, like planets are like the key, like unless we get some information something can live in a star, planets are like usually what people look for. So that's why this is usually a huge part of that. So it's not just like this is helpful for it. It kind of is like the first thing people would do, or the first thing I guess like the people at NASA would actually do in programs such as like that search. And in terms of where the machine learning comes in, this was kind of brought in by astronomers like Dr. Vanderburg, Dr. Anstel, because going through all of the data for identifying a planet is like really like painful. And you're right in that there's some cases where it's just difficult for humans to confirm, and you know, having this machine learning algorithm give a better guess, like based off just different layers of the data that we're not sure about ourselves. That's also like it's also like I guess a way to verify or to identify which one of these curves are actually caused by a planet, right? I guess some example I can give is like if like some instrument noise that's also periodic creates a very weird pattern that creates a very weird pattern that could be identified through the data, it would be very painstaking. It would be very painful for a human to do it, right? To identify it. Not only that, it's possible that a human makes mistakes, but the neural network would be able to pick that up.
So I think like both aspects covered, reducing human labor, but also increasing certainty.
Yes, yeah. I'd say yeah, that makes sense as kind of like the goal for using machine learning for this purpose.
Any further questions?
Yeah, what happens to the data after you analyze it?
As of right now, for us, nothing. We just try to generate interest with it by posting it to our website. Obviously, for NASA, for these researchers, they're trying to publish it to NASA, and then if they get like a confirmed planet, then it goes on NASA's list of confirmed planets. It goes to all of these institutions. We have talked with a lot of these researchers, so who knows? One day, if we get a model that's accurate enough, we might get a confirmed planet here or there, and we'll also be able to publish that to the academic institutions.
That would be very cool.
That's what we're hoping as well.
Other questions? So I guess we wrap up now. So it might be good if you leave your email for some. You guys are students, right? You guys are PhD or master students.
Bachelor.
Bachelor, okay, it's fine. Perhaps it's
Bachelor
good
as well.
if Ricky could leave his email for you guys. So if you have any further questions, you can ask him directly, or you can ask me. I can forward it over. But if you guys have interest in this type of technology, you might use it for your own studies or future research. Yeah, feel free to reach out to me or Ricky. I think my contact info, I'll write. Yeah, okay. Ricky already wrote his mail. I'll write mine in the chat as well. Yes. So if you have any further questions about this talk, feel free to just reach out to me and or Ricky directly. And Ricky, any final words?
Thank you for listening. Yeah, again, sharing email is a good idea, because if you have any further questions, if you want to get involved, feel free to contact me for a warmer introduction. Again, Spacelab also, I think there's a way to contact it on the website, but feel free to do it through me. Also, feel free, LinkedIn, probably just look me up. Yeah, aside from that, hope you learned something from this talk. And once again, thank you for listening.
Thank you.
Thank you
All right,
for the
then.
talk and organization.
Sorry?
Thank you for the talk and organization.
Yeah, you're welcome. I mean, it's quite small, but I think it's good because you guys actually can ask a lot of questions and be a bit more involved. But yeah, great. I will then without further ado, then it's the end of the talk. Any further questions, just send an email over. Okay, bye.
Bye.